Hello. Well,
Hello, how are you? I'm gonna make hi Bayou. I'm gonna make Bayou. Reza is which one? Okay, there's Joel and Reza. I'm gonna make you a co-host. Um, Joel, do you need to be co-host to do the live streaming? No? Okay. That's okay. All right. I'm gonna say goodbye for a minute because I have to send out the link to the other attendees. So give me 2 minutes. Okay. Yeah, sure. Was missing. Oh my goodness. It's missing. Oh my God. Okay. Oh boy. All right. Let me get this out and let me send. Do you have it handy? Send it to me and oh boy. Okay, great. Oh, thank you. Oy. Um, hold on. Leave me alone for a few minutes because I'm afraid I'm gonna lose things. Mm, mm, mm. Uh, 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 uh. I wanted to, oh, whoa. I'm afraid I'm gonna close. Oh, Lordy. Okay. Excuse me. And now I have an email I want to send out to the attendees with the Zoom link. It's ready to go. So give me 1 minute here. And drafts. Okay. I want to add bios. Okay. It is going. Like send. Done. Okay, now I'm waiting for you. So Raisin, Joel, are you sending it? Uh-oh. All right, you're sending it to me, and then I'll try to quickly. I don't see it yet. I don't know how that happened, but it happens. Have you sent it? Okay. Okay. I'll tell you how long it takes to get to the other side of the world. Yeah. Okay. So here it is. And yeah. Um, oh, wait, I see. It says presentation videos, ship accents, MP4, and then it has presentation video installation MP4. Both of them are missing. Installation. Okay. All right. So I want to download it. And I hope I can do this while I have save page. And ladies nope. And gentlemen, my name is Joel Herian Setiawanto, okay, and now I'm accompanied with one of my colleagues, okay, Bagus Ramadan, and we are talking. Okay, and now I hope I can do this with the Zoom open to the playlist. Nope, excuse me. Okay. Desktop. I'm just nervous about Uh, I'm wondering, you know what, Joel? Are you still there? I'm really afraid if I start fooling around with YouTube, I'm going to lose the Zoom. So I'm going to ask you to screen share the next one. Okay? We'll put it in the final playlist, but I think it'll be safer that way. Okay. All right. So I'm closing this guy. And now I have to get into Zoom. And where are we with Zoom? Launch, open Zoom USA. And then I have to get my, don't cancel this. And then I want to get ready. How come I don't see anything? Ah, are you still there?
Yeah, we're here.
Okay, hi.
Yes, ma'am.
I don't know why I can't see. Ah, here we are. Okay, so the next thing, well, I don't want to, we're not admitting anyone till 7:45, another few minutes. So don't admit Clayfeed. I know him, but we're not admitting him. What I want to do is get ready for my screen share. So hold on for that and here. And the screen share is it? Yeah. Workshop playlist. Okay. And okay. Okay. Okay, stop. Now, stop this. Move. Okay. Now I'm screen sharing. And
We can't see it yet, though, Roberta.
You know
We're
I have
not
to
seeing
do
your
these
screen
things
share.
going. All right, wait a second. We're stopping this. We are going back to hello, everybody. Sorry about this. It gets a little, okay, I see everyone. Don't let anyone, don't let Clay feed in. And let me get into that screen share mode again. And that is here, I believe. No. Where is the screen share workshop playlist?
There we go.
Okay, there it is. And when
Yes.
it's in about 10 minutes, we'll turn it on. So right now, with the screen share, I can't see the admitting process. So Anthony, I'm relying on you to.
Yep, ma'am. Could
and
you
what
set
I
me?
also want to do.
Could you set me co-host?
Yeah.
Yeah, he's got to be co-host.
Yep.
Yeah, I didn't make you co-host yet because
Yep.
you just
No, we got Ray's as co-host, but
okay, let me make you co-host.
Okay. You might need to make Joel co-host if you wanted him.
Joel is also co-host, but
so you need
Anthony,
to get
let me make you co-host. I'm sorry.
Okay, ma'am.
Here you are. Sorry about that. I thought I had already done it. So you're only admitting the speakers right now. What we also want to do, Anthony, is hide everybody, other than whoever's, speaking somehow. And there's a way of doing it's hide everyone's. Let's see. Well, I could hide the self view. Let's see what happens. That means everybody else is showing. Boy, Clayfeed really wants in. I know him for a while, but he's not a speaker. Okay. Spotlighted your video for everyone. Okay.
Yeah. I will set the spotlight for the
Can
speaker.
you speak a little louder? I'm sorry. Oh wait, I had it. Yeah, go ahead.
Yeah. I will set the spotlight for the speaker if he or she will present it. During
Okay.
present it, I will, so everyone can see the video.
Excellent.
Okay.
Okay. Okay. So it is now 19:36 on my clock. So in 9 minutes, we'll start this, and we play the music 3 times. It's a 5-minute musical interlude, and then we go into May. Now, where is Alaic in the room?
I don't see him yet.
No, I don't need. Okay, so Alaic will say a few words, and we'll go back to the to Joe. And okay. And all right, we're doing it. I know.
I'm holding on to the edge of my seat.
I know, me too. I kept seeing little typos in my presentations. I think I did it about 6 times. And one of the typos was leaving out the apostrophe for Lloyd's, and they made a big point of it. Yeah. So we're good with Lloyd's. Okay. Okay. So I would love to speak to Alaic, but before we go live-ish. Okay. Well, I think it looks good altogether. So exciting. Okay. I'm staring at a screen. So you know. Clayfeed. No, not yet. Let's see, who else wants to come in? Let's see.
Yeah, people starting to come
Oh
in.
yeah. So none of them yet. Not yet. I know their name. I recognize their names, but we said 15 minutes before, and I want to keep that. I just wish Alaic would come in. That was Brian. That might be.
And ladies and gentlemen, my name is Joel Herian Setiawanto, and now I'm approaching with one of my colleagues.
Okay.
Maybe speaker.
And we are prepared as
we'll
our
invite.
goal is
we're
to
letting him
explain
in.
about collecting weather data RS-422, all the installation of the
Okay. Hello, Brian.
AIS receiver can be shown.
Okay. And another 6 minutes. No, that's 6 minutes. And then just wish Alaic would come in.
I will chat Mr. Alec, ma'am, to coming.
Alec, good. Hmm. Two people entered the waiting room. Nope. Nobody we're waiting for. Goes two ways. Yeah. Okay. 4 minutes. And when the music starts, you can start letting people in. It will be another now 3 minutes.
Okay, ma'am.
Anthony, even though the music will be playing when Alea comes in, let him, give me just let me know. Okay.
Okay. I will let you know if Mr. Alec entered the room.
You never can tell. If some reason he couldn't come in, I'll need to finesse that. So thanks.
Okay, ma'am.
Okay, thank you. Okay, and Harry, we're about to start. So, okay, my husband just came home and he's closing the door. Okay, let's see. It is another 2 minutes, and then we start. Okay. Dun, 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 dun. Dun, dun, dun. Okay. In a minute. Last off. All right, less than a minute.
But we're not seeing the scene yet, though. Should there be a scene with the music? Yeah, no, I just see the white page with the address. So you got to change this. Yeah, when the YouTube starts, you got to switch your screen share to the video.
Wait, stop share. Okay, and then I have to, 1 second, okay. Wait, I have to do screen, okay, right, screen share. Oh, wait a second. Okay, 1 second.
Yeah, now screen share. Yeah.
Now you see, no, but I don't know.
Not yet. Not yet. Yeah, but screen share once it starts to play.
Screen share. Okay. 1 second.
Good morning.
Okay, let me stop again and screen share. Okay. Okay. Okay, and let's see. I have to go to screen share. Now, why can't I get to, am I still on?
Yes,
We're just still seeing
Yes,
you.
You're still seeing me. Then
Yeah.
I am going to give, I'm going to give this to Anthony again. I'm sending, here's the link.
Okay, ma'am.
Okay, I'm going to send it to you. And when we play the music, we play it 3 times.
Okay, ma'am.
All right.
Where you send the links?
I'm going to send the link to you, which
Yes.
I did before. So this is the link for the playlist. I'm going to send it right now.
Yep. Please send me. I will play immediately.
Okay. Here's the link. 1 second. Paste and send. Okay. And all right. So you have it. And the music goes 3 times. So I'm going to get out of the playlist this second and go back into
Do you send me a link in the chat box or email?
No, I sent it to you by email.
Oh, okay. I get it.
Okay.
Just got it.
I didn't want to send it by chat box.
Okay.
So this is the playlist. Hello, Greg.
Hello, Roberta.
How are you?
Good, thanks.
Good. Little technical. All right. So 4 people have entered the waiting room.
There we go.
All right. You play music? Great.
Could you skip? Okay.
Okay, now we can let them in. So you play the music. Do it 3 times. I'll be letting them in.
Okay.
Elizabeth. Oh, that's Doug's wife. Okay. Somebody I don't know. Oh, I know who it is. Okay. Good.
Could you hear the music?
We're not hearing.
Could you hear the music?
No, we don't hear the music.
We're not hearing the music.
Oh, wait a second. I will share screen, and then how about now?
There we go. Now,
okay,
we got it.
great.
Thank you.
Okay.
Okay, play it again, please. Thanks.
Yes, ma'am. I will play again.
time, please? Okay, so now we'll start the playlist, and after the first presentation, we'll leave space for Laic to say a few words.
Ma'am Roberta, could you make Mr. Alec co-host?
Okay, sure. Where is he? Okay, I don't seem to find Laic. There he is. Okay, sure. Okay. And so play the next piece on the playlist, and then we'll stop for Laic to say a few words. Okay, Anthony?
Ma'am, wait a second.
Okay, great.
Everybody.
Thank you.
Wait.
Thank you. I'll mute myself.
Could you see my share screen?
Yes.
Okay, let's see.
Hello. Welcome to this workshop on sudden hazardous maritime weather detection and communication. The workshop is being convened by the Worldwide Ferry Safety Association. I'm Roberta Weisbrod, Executive Director. We will be describing research that was funded by the Lloyd's Register Foundation, for which we are very grateful for the support as well as their encouragement. My job today is to talk about why we're
recording
doing
in
this,
progress.
why sudden hazardous weather, why Indonesia, who we are, and what has been the guiding philosophy for our research. Well, sudden hazardous weather is a major cause of maritime accidents to this day all over the world, including close at home within the past year in the Gulf of Mexico. The ability to understand will help prevent accidents, particularly of our concern, passenger ferries. But it will also feed the global weather models and help predict large-scale weather patterns, very important as the global climate changes. Why Indonesia, the maritime continent, 5,000 kilometers east to west, 1,000 kilometers north to south, 17,000 islands connecting the Indian and Pacific Oceans, 1/8 of the globe's circumference at the equator, incredible hazardous weather, which will be described by Bayu Ido Pratama, who will also discuss approaches that Indonesia is engaging in. And Indonesia's weather affects a large part of the world. Who are we? The team leads are myself and Laic Nurayudi, who is with the Indonesian Government National Transportation Safety Committee. He's also a PhD student at Surabaya ITS. He has his master's from the World Maritime University, and I would say wrote the classic thesis on ferry safety. We have, first and foremost, on maritime weather in Indonesia, Bayu Eto Pratama, who was with the National Weather Service, BMKG. We're joined by 3 students from Surabaya ITS, Anthony Muslim, Joel Herdian, and Reza Bagas Ramadan. They did a large part of the hands-on research, and they also gave us their intellectual firepower, their resourcefulness, their ingenuity, their persistence, and they were totally great to work with. Anthony has already graduated recently. Joel is on his way to graduate. So we recruited 2 new students, Alfarizi and Mohammed, who have been apprenticing to the other students and will keep what we're doing sustainable into the future. So we're looking forward to working with them. In the US, we have at the University of Albany 2 data scientists, Dr. George Berg and Dr. Catherine Lawson. We've been working with them for several years on weather projects, and it's great to be working with them now. And hopefully into the future. Also with us are Dr. Paul Casera, who with Martin Steinson has been working on 3D printed automated weather stations. The team was guided by Brian Tetrault and Dr. Gregory Johnson. Brian's work will have a profound effect on understanding global maritime weather. He'll be describing his work. Gregory Johnson is his consultant, and we can't say enough to thank Greg, for his assistance in guiding us as we assembled the equipment. His patience was extraordinary, and he was amazingly helpful. So we're very appreciative. And I will also say that Joe Sienkiewicz, who will also be speaking, is someone who has been very gracious with his ideas and encouragement over the last few years. So again, we appreciate you as you know, Joe. Research, philosophy, and protocol to understand and predict local maritime weather. We archive data at the site of accidents and look at the weather information before and during the accident to see if there were any signals that would give us a hint of changes in the weather that would help us in nowcasting weather at certain sites and help prevent accidents. And we got the archive weather information from weather stations in Indonesia, usually, but not only land-based, and from satellites. We also came to the conclusion that we needed to set up a system to get vessel route-based data, and we looked at the concept of 3D printed automated weather stations and using commercially obtained weather stations connected to AIS. And finally, we're prepared to analyze the data to help set up an alert system. We'll be starting with the Corps' pilot project data and then take the data that we will obtain from this research as it goes forward. So with that, I will say thank you for your attention. I will pass it over to Alaic Nurwayudi, who will say a few words, and after that, Joe Sienkiewicz will give the big picture of on how to understand global weather. Okay, so Alaic, would you like to introduce yourself for a minute and then? Okay, great.
Okay, can you see my
yes.
screen now, right? All right. Says, all right. First of all, thank you very much, Dr. Roberta, for the introductions, and I owe you a big thank you that this project has focusing and selecting Indonesia for as a pilot project, I presume. Just want to add more why we feel very confident that Indonesia is the perfect role model for this particular project that Roberta mentions that yes, we are maritime nations. Roberta mentioned that we are maritime continent, in fact. So then again, I just want to emphasize again that we have very strong maritime culture that, in the old days, our ancient was traveling 8,000 kilometers from Makassar, which is in the central of Indonesia, bound to west up to the Madagascar island. And that was a very amazing trip. And we have historical achievement for Sriwijaya and Majapahit Empire in the past, that they also developed very strong fleet, and which is continued by another empire, and they also understand the importance of maritime situation of in Indonesia, but Nusantara at the time that we called. Then again, Related to current situation, Indonesia is now in the top 5 of seafarer supplier country for the whole international fleets. So for that reasons, our government again improving our maritime transportation system and networks by developing numbers of programs such as Pioneer Line program, CTOL program, expanding the ferry lanes not just for short road but also long road of the ferries. And in addition to that, we have massive fleets. For example, like we have more than 470 registered ferries, more than 29,000 merchant vessels, with another 50,000 fishing vessels, with supported by more than 2.6 thousand ports and terminals. In fact, data in 2020 indicates that there are 2.4 billion tons of cargoes transported using maritime or shipping operation in Indonesia. So then, as you can see, this is actually the AI-based traffic profile, which is in 2021. Under this geological situation of Indonesia, Indonesia has played a significant role in international maritime. So therefore, our president is declared that Indonesia as national maritime fulcrum. Then we are developing numbers of advancement and improvement in many sectors. So then. Yes, I think Bayu will explain this much better, relevant with the weather situation and how it's important to the sustainability and then connectivity of Indonesian shippings. For that reasons, again, we are very delighted and thankful to again to WFSA by choosing Indonesia as a role model, and I believe that the advancement of this project can be also adopted by other region or countries, so they can also see the benefit of.
Uh-oh. Uh-oh.
I think Mr. Eilek is disconnecting.
Oh. Uh-oh. What are we doing? Anthony, do you want to keep, I don't know what happened. Do you want to just keep moving?
Okay, ma'am.
Yeah, and
okay.
let's go to Joe and we'll pick it up later.
Okay,
okay,
everybody. I think Mr. Eilek is just disconnecting, and then I will play the next presentations. Wait.
So going back to the playlist. Okay, great. Thank you.
Hi, my name is Joe Sienkiewicz, and I work for NOAA at the Ocean Prediction Center, where we're responsible for marine weather warnings and forecasts for both the North Atlantic and the North Pacific. So I'm going to talk today about maritime weather from 36,000 kilometers above the Earth's surface. In other words, from geostationary satellites, and talk about the utilization and limitations of satellite data to the marine forecasting problem. So what's changed over the last couple of years? We're kind of in an evolution that short-term decision-making can now be better done using satellite imagery. And part of the rationale for the reasons for that are the rapid availability to forecasters of the data. There was a reduced data latency, that we're no longer getting data that's 20 minutes old, 40 minutes old, where a storm system, thunderstorms complex, convection complex, existed and then has faded. We can visualize, for a variety of different reasons, I'll go into that in the next slide, time rate of change of the atmosphere. data acquisition of the data is relevant. It requires minimal interpretation. A lot of decisions went into deciding what channels, what bands to sense the Earth's surface and all. And the last one is that forecasters are trained on the capabilities, and that's really critical. That way they're not trying to learn on the fly, but are actually trained and have expectations in how to use data. Also, the next step is basically artificial intelligence and designing and developing tools that then can be used with forecasters to start at a higher level in the decision process. And as an example of some of the advancements, down in the lower right is a target area over a intensifying tropical cyclone in the western North Pacific, and at 2.5 minute imagery. A visible image, and actually I think it's a visible image, and you can see basically the detail and actually see how the storm is changing. So what has changed? It really is about the imager. Basically, for the Himawari satellite, it's called AHI, and for the geostationary GOES series of satellites, it's ABI, Advanced Baseline Imager. And the resolution is much higher for all of the channels that have been in the past, for all the capabilities, whether it be visible, infrared, or water vapor, which in essence is an infrared, both in the horizontal resolution, but in the case of the infrared, in the vertical. There are many more channels, or also called bands, and it allows for the development of products using multiple channels. And here are the list of a number of channels that are focused in different areas: visible, near infrared, and infrared. And the Himawari capability and the GOES-R capability are quite similar, because in essence they're the same imager with just some slight differences, and you can see the differences there. I've also included links in this. So the Himawari and GOES-R, if you're curious, there are pages that are linked right there that you can go to and learn a lot about what the capabilities are. The temporal sampling has changed. For full disk now, they're both GOES and Himawari are producing images every 10 minutes. GOES over the United States is at 5 minutes, where Himawari over Japan is at 2.5 minutes. And they also have a target area, which is what I showed in the first slide, of 2.5 minutes, and landmark areas of 30 seconds. On the US side, we have mesosectors, which are 1 minute, and 2.5, which is the target area, is 2.5 for Himawari. The limited latency to ground system and distribution is absolutely critical. So in other words, the data is fresh, it's new, and it's relevant, and that's really critical and a game changer. No longer waiting for data like we used to in terms of anyway. So a latency, reducing the latency means you're making decisions on nearly real-time data. So I'm going to give one example of, on the US side, of something we're working on. It's called Prob Severe Lightning Cast, or LC. And it was developed at the Cooperative Institute for Meteorological Satellite Studies at the University of Wisconsin, and uses geostationary lightning mapper data, another instrument on the GOES series of satellites. It is an imager, and the field that it's using is flash extent density. So it's designed to predict lightning out to 1 hour. And it is proving itself to be useful for offshore thunderstorms in a probabilistic sense. And the example here shows basic contours and probabilities of lightning occurring within the next hour. So the potential uses beyond US Doppler radar network, such as in offshore waters. And if you think about it, lightning is a proxy for convection for high winds, waves, and possibly reduced visibility and high rain. It is neural network based, machine learning trained from both imagery. It matches the textures and picture values, but also to the global lightning mapper flash density within the next hour. So there's a growing use of geostationary imagery and products for short-term forecast decisions. It's facilitated or buoyed by satellite capabilities and reduced data latency. It doesn't solve all the challenges. Fog and reduced visibility still is a challenge, especially when there is a high-level cloud masking the low cloud, and also determining whether a stratus cloud or is fog. Thunderstorm detection, yes, but the associated conditions remain challenging. And it does reveal the complexity of the fluid of the atmosphere and ocean, and in some ways can make interpretation and resulting decisions more challenging. But we're all learning together. Thank you very much.
Okay, just information. Member Berta, your mic still mute. In mute.
Next on the playlist, keep going. I believe it's Bayu and Alaic, and then we'll have a question and answer session. So if you can pull on the playlist, please, Anthony.
Okay, thank you. Good morning to our colleagues from Indonesia and good evening to our colleagues from US. First of all, I would like to extend our thankful to Worldwide Ferry Safety Association, especially for Dr. Roberta, who has invited the BMKG to involve on this workshop. And I would like to introduce myself. My name is Bayu Pratama. I'm from Marine Meteorology Center of BMKG, the Indonesian Agency for Meteorology, Climatology, and Geophysics. And today I would like to deliver about the marine weather condition over the Indonesian seas. Please let me to share my screen. As we know that Indonesian seas play an important role and strategic position between the Indian Ocean and Pacific Ocean, and also between the Asia and Australia continental. And the complex of land and sea distribution and topography make a prediction of high impact events in this region extremely challenging. Furthermore, global and regional factors influence the weather and climate patterns in Indonesia, such as the Asia and Australian monsoons, and also the phenomena in the Indian Ocean, such as the Indian Ocean Dipole or IOD, and also the Madden-Julian Oscillation, which is moving from western part of Indian Ocean to east and across the Indonesian seas. And also the changing sea surface temperature in the Pacific Ocean, as we know, the ENSO phenomena, or El Nino and La Nina, and also the tropical cyclone in the Indian Ocean, southern part of Indonesia, and also the tropical cyclone over the Pacific Ocean. And this phenomena can cause extreme weather condition in Indonesian waters, such as high waves, the extreme wave, and also the strong winds and storm surge, and also the water spout and inundation for the coastal community and so on. And according to the survey from United Nations Conference on Threat and Development 2017, that agree that several weather parameters have a significant impact on sea transportation, including the temperature, the fog and rain related to the visibility, and also the wind condition, the wave and sea level, and etc. And based on this correspondence, we agree that wind and weather condition and waves are the most influential weather parameters. And also based on that information, we can conclude that weather has a significant impact on the safety of sea transportation. For example, in several parameters like sea level, mean sea level changes will be impact to damage in port infrastructure and cargo, and also the temperature, the precipitation and fog, and also the wind. For example, the extreme harbor wind will be impact on a problem in sea support navigation and berthing, and also the operational disruption due to inability to load and unload. And in this session, I would like also to demonstrate how critical observational data at sea is for marine transportation safety. It's a case study in KM Lestari Maju. KM Lestari Maju sunk in Selayar waters around 3rd of July 2018, around 5 UTC, and based on the marinetraffic.com, we can inform that the distribution of ships in the water surrounding Selayar Island have a large number of ships were observed passing through the Selayar waters area, but only one ship reported the real-time weather condition, which is the KM Tilong Kabila, which is already installed by BMKG, the vessel automatic weather station. And we agree that the data is extremely useful for providing the early warning to ships and areas prone to the severe weather. And also from the data from the KM Tilong Kabila, we can get the information, the air pressure pattern has changed significantly since 03 UTC, and also the wind speed has changed significantly up to 13.5 meter per second or 26 knot. And we can imagine that if all the ships that were sailing observe the weather and send the data in real time so that the other ships could access it, the ship could immediately change course to avoid the bad weather, right? So we hope in this workshop we can develop a recommendation for how weather data on ships can be widely used by the other ships. Okay, thank you for having me. Good morning.
All right, thank you, Roberto, for the time and opportunity given to me. Good morning, good afternoon, and good evening, ladies and gentlemen, dear all attendees. In this session, I would like to present to you the topic of weather contribution to the domestic rural ferry casualty. I understand many of you has expertise on this matter and perhaps has different perspective on this topic. That would be fine for me, as it will enrich our discussion. Please note that the time for covering this topic is so limited, so I will speak mostly on the weather related to rural ferry casualty. As I mentioned in the title slide, that my presentation focusing on rural ferry operations. So the rural ferry is one of among different types of ferry. A ferry is considered having its own technical characteristics to support its operation pattern. For the purpose of carrying the vehicles in an affordable number, the ship is designed to have a continuous deck over its entire length. A rural ferry can also be easily identified by its rams, which that are located either at its forward or after ends, or on its side. The rams work as a connecting means for vehicles from the port to the ships. The rural ferry also can be notified by its higher or larger air draft and higher beam to draft ratio. Passenger rural ferry also has lower freeboard, and then it has highly maneuverable propulsive systems, as well as it has a distinct cargo securing system. So to understand how ships perform during its voyage in water, the following terminology is generally used, such as seakeeping is defined as the ability of a vessel to endure rough conditions at sea and navigate safely during long storms. Ocean is considered as an external energy that affects the performance of the ships. In the analysis, it is referred to as the energy encounter frequency. Ocean waves can work in the form of regular and irregular states. When seawater reaches decks, it is considered as an additional load. So every movement of ocean waves, the ship will respond by moving according to the 6 degrees of freedom, which is called response amplitude operator. When the ship moves at large angle at relatively high speed, there is an additional load which is known as wave impact load or slamming. In ship design, the following ratios of ship dimensions are used. Higher value of length between breadth is suitable for a higher speed operation vessel and provide good cargo compartment ratio, but it will reduce the ship maneuverability and ship stability. For a smaller ratio between length and beam, it will provide better stability and increasing ship stability. Ratio between length and height mainly related to the ship's longitudinal strength. Higher value of length with the height will reduce the longitudinal strength. Ratio of height and draft related to the ship reserve buoyancy. Higher height to the draft mostly for passenger vessels. Lower beam to draft might reduce ship stability, whereas higher beam to draft would improve the stability but increasing ship resistance. Ferry is commonly known as a higher beam to draft ratio. Understanding the ship maneuvering characteristics is also important to see how the ship was handled during heavy weather conditions. Ship maneuvering performance influenced by its underwater hull geometry, pivot point, lateral motion, propulsive system, thrust and factoring devices such as bow thrusters. In viewing ships with a critical situation when dealing with the heavy weather, there are three main critical conditions, such as heeling, capsize, and sunk. Again, ship will respond to the external force by moving against it. Ships would heel accordingly as react to the external force such as wind and wave. Heel is temporary inclination of ships caused by outside force such as winds, waves, and during ship's turns. Capsize took place when the uprighting moment is no longer exists or less to the heeling moment to hold the ships. Ship would capsize when the righting moment is reduced due to shifting of gravity point toward or exceed its metacentric point. When the gravity point exceeds its metacentric, uprighting moment turn into heeling moment and would rather accelerate the heeling rate. Sunk is considered as loss of ship buoyancy due to additional ship load, so the fluid surrounding could no longer provide enough force to keep ship afloat. During these conditions, the ship displacement is increased by all constituents. Having more water inside is the main cause of this condition. Since 2003, KNKT has investigated 53 cases involving ro-ro ferries. Not all cases contributed by weather condition, but cases of capsize, grounding, and small number of collision found that influenced by the weather status. All aspects of ship operation and environmental state is viewed and considered when analyzing the cause of an accident. However, KNKT considered that the weather was not the main cause of the accident, but rather increasing the condition of accident to take place. This chart presents location of accident during 2003 to 2020, which is selected by weather contribution to the accident, not just for ferry, but in many cases investigated by the KNKT. As you can see that inside the red oval line, the numbers of cases took place which is contributed by the weather. So to sum up, I've mentioned above, there are many ways weather contribute to the accident, but it can be categorized into followings. Affecting stability issues, heeling moment exceeding its uprighting moment, strong wind and high waves might contribute to the loss of the stability. This caused by a number of factors like a shifting of the ship's internal part and as well as a free surface moment. The next one is affecting ship's buoyancy, low freeboard increasing probability of seawater to enter and flood the main deck. Then adding ship's displacement. affecting seakeeping and maneuver, damage to the structure due to slamming, combination and strong end wind and current affecting ship maneuvering performance. On the other perspective, weather can also create excessive rolling, which is affecting passengers' comfort. Parametric rolling could take place when the ship natural rolling resonate with the sea frequency. In addition to that, heavy rolling as a result of parametric rolling resulting in internal rolling condition as shown in the right side of video that the truck is trying to escape by themselves, then it might also shifting internal part of the vessels and affect ship stability and seakeeping performance in general. To conclude my presentation and based following information and findings above, there are points to note so relevant parties might consider to think about. First one is weather is a given condition. So we cannot change the weather unless you have ability to do that. So act accordingly. So, and then the ship will behave accordingly following its input and maneuver, such as like maneuvering, handling, and thrust level, and also sea stage. The hull shape and ship dimension is characterizing ship response to the input, whereas the shape ratio can be used to determine the likelihood of ship performance in various weather conditions. So this condition can be used as well to do the risk assessment in analyzing safety of ship operation in different kind of weather. And last but not least, understanding ship operation limits in heavy weather is important. Therefore, the ship's crew need to have access to current and forecast weather information and included in the passage planning considerations. Crew also required to familiarize themselves with the ship states, like a loading limit, performance characteristic of vessel in maneuvering, and etc. Weather condition in the operating region is also has to be known by the ship's crew so they can design the operation safely. That's all for my presentation. I understand this time is very limited, so I look forward for further fruitful discussion and during question and answer session. Thank you very much for.
Yeah, thank you. And now is time for questions. And Alaic, if you would like to field the questions. I know I'll kick off the ball because of my curiosity, if it's okay. Bayu, I noticed that there was a place where there was cold water infusion north of Java. Could you explain that?
Yeah, Roberta, regarding the monsoon. Yeah, the cold is the cold temperature that occur on the China territorial, and the wind will bring the cold temperature to the Indonesian seas. Will be effect to the weather the effective clothes over the test, Roberta.
Okay, thank you. I'll probably ask you a little more about that. Thank you. Does anyone else? Who else has questions? Do we?
Roberta, yes, if I can comment. Yeah, Captain Nur Rahman, a member of the Worldwide Ferry Safety Association Board. First of all, I want to thank all the panelists, all the speakers who spoke on this, all excellent ideas. But my question is more or less focused, or I need to get some information from Joe Cianca on his satellite nowcast weather. Now, the Lloyd's Register Foundation, as we all know, has categorized 3 countries as the worst maritime disasters: Philippines, Indonesia, and Bangladesh. And let's go to Bangladesh. Bangladesh is almost 98% inland waterways where there's no sea involved. this nowcast weather is very, very important to these people. If as I have listened to Joe's presentation, if one can see or predict the tornadoes or strong winds in a small place of play, stretch of sea or inland waterways, it will really help the ferry operators to work. Now, my question rises here, and maybe it will come later on in the session, is how to transmit this newfound information to the ship's captain or ship's crew in order for them to make a decision. I don't know if Joe can help me on that one.
Thank you, Captain. I appreciate the question, and yes, it's a challenging one. What I tried to do, I described an issue that we have in my own country, basically of thunderstorm activity beyond our Doppler radar network, and there are means, for instance, to transmit information under a global maritime distress safety system. And in fact, we had a recent incident of a lift boat in the Gulf of Mexico that capsized, actually within our coastal zone and within the radar network. The NAVTEX requirement of the medium frequency, that, as it turns out, that, and I know it's still under investigation, but there may have been an issue with the transmission of NAVTEX. But there are other means within our own nation that don't exist. For instance, VHF radio. We have a network in the United States across the country of VHF called NOAA Weather Radio, and it's an all hazards radio. And when an incident occurs or is anticipated to occur, a forecast for a warning, then that basically is what is broadcast as soon as the warning is issued or within seconds of when it is issued. For instance, a tornado problem, meteorological centers. Now, from the meteorological centers, obviously, is the next step in order to communicate out. And as I understand, NAVTEX is the primary method for coastal zone or near shore zones, with the Met area forecast being larger, which really don't focus necessarily in the time frames that you're talking about, especially when it comes to inland rivers and all. So there has to be some form of communication. In the future, there is something called S100, which is the International Standard Hydrographic Standard for charting. And part of S100 is the weather portrayal of weather hazards, of observations, and of what we call either graphics, or we call it conditions, but graphics or gridded information. So the type of warning that you're discussing basically is that you're asking about would be a hazard, a thunderstorm warning, an area of expected winds. So that and would be in a polygon form and described that way, with the ability to be displayed in electronic charting systems, including ECDIS. This is a lot of work, and it's going to take a decade maybe for implementation. My own office is actually working on the weather portrayals for larger scale hazards, but we in the United States we're in the beginning of doing polygons for smaller time scale, such as thunderstorm areas. And typically we overwarn by counties is the description. So we basically describe a warning for a defined area within a state. And unfortunately, if you're in a large county and there's a warning in your county, yet the storm is in, say, the south part of a county, then you're not really in a threat area. So polygons actually are the way that we're looking to do that, to devise a way to create polygons and then also to distribute polygons. Now, that's still a discussion point in the marine world as to how they're going to be distributed. I'm not so sure I actually answered your question, but
No. Thank you very much. Excellent.
Right.
I got some input, but because of the time, what I will do is I will go offline sometimes and speak to you, because I think I'm very interested in what you presented, and we can develop it from there. Thank you very much.
Thank you, Captain.
Nura, in response to the river system of Bangladesh, we just learned from Paul Casera that University of Dhaka is starting to build 3D printed weather stations. So they could be applied to an AIS program, such as Brian and Greg will be describing. So just as a narrow response to your question.
So, sorry, Roberta. I might have bolted before the cart. Anyway, I'll listen to Paul Casera later on. Thanks very much.
Thank you. I think we probably have used up our question period nearly. Nura, do you have any remarks or questions you'd like to ask at this point? Or should we?
No, that's all right from me. Please continue. Thank you.
Okay, great. Should we take Anthony? If I don't see any more questions here, and by the way, if people have questions, either put them in the chat, or you can, if tomorrow you think of a question you want to send it to ferrysafety@gmail.com. We'll field the questions. We absolutely welcome the questions and the responses. So now I think unless anyone has any objection, we'll go on to the next section of the playlist, Anthony.
Okay, ma'am. I will share screen again, everybody.
Thank you, sir.
Oh, wait a second.
Good afternoon, good morning, or good evening, depending on where you're watching this from. My name is Brian Tetro. I'm with the U.S. Army Corps of Engineers Research and Development Center, and I'm going to talk about a concept that we've been working on to collect automatically weather observations from ships and transmit them via the ship's AIS system so that they can be received and used in weather forecasts. The background on this is that currently ships provide some weather observations voluntarily. More observations make better forecasts. However, it's a small fraction of the vessels that are out there that are actually providing observations. On the left image, you can see a plot of the North Pacific Ocean with voluntarily reported weather observations. And on the right-hand side is a snapshot of the same area with indication of vessels' AIS positions received via satellite. And you can see that there's a substantial larger number of vessels out there that are potential platforms for providing observations. These are done voluntarily. They're done by the mate on watch, who often can have other things, and they're only collected 3 or 4 times a day. What we're looking at is the concept to collect weather observations from ships via AIS. And so out on the ocean, you've got a ship. They've got the mate on board, and ideally have some weather sensors. We have a computer that can collect either in manual input, but primarily from automatic sensors on board the vessel, collect weather observations. And then it creates a AIS message out of that it presents to the regular shipboard AIS transceiver that then transmits it. The weather observation could be received by other nearby ships, could be received by a shore AIS network, or by AIS receivers aboard satellite. However the data is received, it can then be routed through an AIS network, placed in a database where the AIS messages can be processed, decoded to extract the weather information. Perhaps some quality assurance could be applied at this point, and then placed into an observation database for access by the forecast models and weather forecasters to use in their forecasts. So this is a concept. What I'm going to talk about for the rest of this program is what we've done to date to test the concept and some of the initial successes we've had. So back in 2018, we tested it in a laboratory environment to prove that it worked, at least in a lab environment. Then we went on board a ship In this case, it was the U.S. vessel, the Cape Wrath, provided by our Maritime Administration. And this, we were able to do a real world test of using the ship's AIS. A weather station up in the upper right-hand side is a weather station that we installed aboard. And then we let it transmit for a couple of weeks and collected the data from a shoreside AIS receiver that we had. And we proved the ability that we could create the AIS messages, present them to the ship's transceiver, that they could be transmitted and received ashore. So the next step was then to go on a ship that was actually going to sail. And again, through the Maritime Administration, we got on board a training ship that was doing their winter cruise from Massachusetts down to the Caribbean and back for 2 months. And so we didn't have any attending there. We gave the crew a little bit of training, but they really didn't have to do that much. And then set up the equipment on board. You can see in the lower middle, the setup that we had, where we have the AIS laptop computer. In this case, it's a laptop. You'll see later that when Greg talks that we're using a different computer now. It's hooked up to the weather station, which in this case was mounted on the bulkhead in the chart room, and then connected to the AIS via the pilot port. And we just let this run. There was one problem we had with a Windows issue that we had to fix halfway through the trip. But on the far lower right-hand side, you can see the position reports, which are in black, and then the weather reports that we received from the vessel. This is all via satellite reception during the trip. So we considered it quite a success and decided to expand. And what we've got now is we've got installations aboard about 16 different commercial vessels that are listed here. They're running on a variety of different routes, Trans-Pacific, Transatlantic, US Great Lakes. One's a research vessel, it kind of goes wherever. And then we've recently added a couple of near-shore ferries running in the northeastern United States, as well as working with the Malaysian government to install on a ferry there and get that working. And then we also, very interestingly, have teamed up with IBM and some other researchers who are running an autonomous vessel across the Atlantic Ocean later this year. It's called the Mayflower 400. And so we're really looking forward to see how this operates on an autonomous vessel. One thing with AIS is you have different sizes of messages. And so basically the shorter the message, the better chances it will be received. So we're testing 6 different messages. 3 that are in blue in here already existed. We're in IMO documentation, but then we created 3 other ones that were much smaller to increase their chances of being received via satellite AIS. So far, our findings have been quite promising. The installation is fairly simple and reliable. We've gotten positive response from the maritime industry. Almost every captain that we've talked to has been very excited about it and eager to participate. And we've successfully demonstrated receipt of observations via both terrestrial and satellite AIS. We're delivering the observations to the National Weather Service. That took a little bit of work, but we finally got a fairly good process in place to deliver them to the Weather Service. And we're doing initial analysis of the effectiveness, some of which you'll see here. So first off, this was a plot of over a year's worth of the weather observations that we received from the participating ships, all received via satellite, I should say. And then this was from one particular vessel in that same time period. And you can see the different message types. There's a higher reception rate of the smaller AIS messages. So for example, the FI-25 is the green one, and you can see it has much higher peaks than the FI-33, which is the light blue one, which is much lower. Also, you can see in this case, there was a period when we didn't receive data from the vessel. And it wasn't that the system wasn't working, it was that they were in the far eastern Asian waters where there's lots of AIS congestion, which also reduces, and in this case, pretty much eliminates the possibility of reception via satellite. Well, that's a real quick overview. I know I have only had a short time here, so thank you very much, and I look forward to your questions.
Greetings to you in whatever part of the day you happen to be watching this video. My name is Dr. Gregory Johnson, and I'm going to be talking to you about the Weather over AIS system we have developed and prototyped. This project has been funded by the United States Army Corps of Engineers. I will mention some specific products during this presentation, the things that we have used. This is not to be construed as any sort of product endorsement. If you're interested in these AIS weather systems we have developed, my contact information is at the end of the presentation. The primary component is the AWS, or Automated Weather Station. You can see that we've selected one here from Airmar, the 220WX. This has a variety of sensors so that we can get wind speed and direction, position, time, course and speed over ground, heading, pitch and roll, angles and rates, temperature, pressure, and relative humidity. All of that data is output as NMEA sentences over RS-422 serial. This will show you typical AWS installations that we have done on commercial vessels, where the weather station is mounted typically up on the flying bridge or on top of the pilot house, either mounted to a rail, mounted to an extender post attached on a flush mount surface, or to an existing post. The key point is to have the weather station in an area where the clear view of the sky for the GPS, as well as clear unimpeded flow of air for the wind speed measurement. The second component is a small computer. Here we're using a small embedded processor from Moxa, and this computer is running some custom software that parses the data from the sentences from the weather station and packages those into AIS application-specific messages, or ASMs. We're transmitting a variety of these for testing purposes, from small being a satellite ship weather report that's only 1 slot long, to the largest being an FI-33 environmental message, which is 3 slots. We're also a middle-sized one is the ship weather report, FI-21. All of this data is put into an NMEA BBM sentence, broadcast binary message, which is pushed to the AIS transponder over an RS-422 serial connection. The computer also receives data from the AIS, which gives it a record of all of the messages that are transmitted and received by the AIS. Typical installation of the computer, because it's very small and lightweight, is we typically just Velcro it to a bulkhead. You can see here some various mountings here on the wall. In the back side of the pilot house, here's mounted on the wall on the front of a pilot house and on the side of a cabinet. The final component is the AIS system, and here we typically use the ship's already installed AIS. The AIS receives the data in the NMEA sentences and then transmits the messages over the VHF channel AIS 1 or 2 as an AIS message 8 using random access TDMA mode. And all of the messages that the AIS receives and transmits are pushed back to the computer in the NMEA sentences. There's 2 connection methods we've used for the AIS. The easiest is to use a pilot plug. Solus class vessels are required to have a pilot port available for pilots to plug into, and that makes for an easy connection. And we usually install a Y connector so that there's still the ability for the pilots to plug in when necessary. But we can also connect directly into the AIS transponder. Pretty much all AIS transponders have a junction box with a terminal strip, and it's very easy to wire directly into that as well. So now looking at the receive side of this, all of those AIS messages that are being transmitted are received via either satellite or terrestrial receivers. For our effort with the Army Corps of Engineers, MERIT, and NOAA, we would take these received messages, we run them through a computer process to pull the data out of them, and forward that data to NOAA for use in weather forecasting. However, those AIS messages are also received by other vessels, and that's probably of more interest to the Worldwide Ferry Safety Association in this effort here, is that other vessels receive this weather data and can see that. So although the AIS message 8 is not displayed on the AIS unit itself, by standard, this data is output to the presentation interface for display. The messages are displayed on some ECDIS and electronic charting systems, and there's a couple references here for guidelines for manufacturers on how that information should be displayed. This gives an example of one of the systems that displays these type of messages. This is the Rose Point ECS, and you can see here a vessel. This is the Block Island Ferry, the Block Island. And you can see this little yellow dot indicates the weather message, and it's a little tough to see in this picture, but you can see the wind speed using a standard weather vane indicator of direction, and with the flags indicating the strength, and you've got the temperature showing there as well. The pilot project I mentioned for the Army Corps of Engineers, MARAD, and NOAA was involved putting these systems on various commercial vessels operating out in the open ocean, primarily receiving the data via satellite feed, and then taking this data and processing it to get it into the NOAA weather system via the GTS. And that way it is available to weather forecasters to improve weather forecasting. It just shows an example of the various vessels that we currently have this system installed on, operating all across the world. I think we are up to about 14 vessels now. And this is an example of locations of where data has been collected from all of the ships over 2020 and 2021. So we have been getting pretty good coverage, weather data from all across the world. Thank you, and here's my contact information. I hope you've enjoyed this presentation.
Hello everybody, my name is Imam Antoni Muslim. Today I would like to present to you about one of the methods that we use it in Ferry Sudden Hazard research. The method is using existing archive information, climate data store Copernicus to analyze ferry accidents due to sudden hazard weather. The outlines that I would like to talk are first, what is the climate data store Copernicus? Second, I would like to talk about ERA5 Copernicus dataset inside the climate data store. And next, what kind of data ERA5 Copernicus. And next, about the processing the Copernicus dataset and how comparison between the result Copernicus data and accident data. And the last is conclusion. Climate Data Store Copernicus is a free and open source data from Copernicus that we can access from Copernicus Climate Change Service website. The website is cds.climate.copernicus.au. And in this research, we use ERA5 hourly data on single levels from 1979 to the present dataset to analyze the sudden hazard weather case on ferry incident in Indonesia. And ERA5 Copernicus dataset or ECMWF reanalysis version 5 is the latest climate reanalysis dataset that produced by European Center for Medium Range Weather Forecasts. It provides hourly data on many atmospheric, land surface, and sea state parameters. And what kind of the data from ERA5 Copernicus? The ERA5 has a format data group, and inside the group format, there is gridded data type format that could show us the gridded ordinate at some weather map with some variable. The illustration is in a picture below, and because the data format is a group, we need some software to make processing or view the data inside the data set, and the software that we use it is Panoply. And the Panoply is a cross-platform application that runs on many operating systems, and Panoply plots georeference and other array, especially group data sets. And Panoply can create color contours plot from 2D or larger multidimensional variables. So when you have a group data set, you can open inside the Panoply, and the Panoply will show the parameter that you have chosen inside the website. And then the one of the feature of the Panoply, we can create the video or the photo of the weather map. For instance, this picture. And here is one of our recent analysis in the Treta Prima accident on 11 January 2009. As you can see from Panoply software, we can make interval time video of the weather during or before the incident. And from the video, we can snap a picture in the time that we want. For example, we can snap in the time during the ship wasn't in the port on the picture above, and then we can snap on the when the ship wasn't in the incident time. So we could make analyze the weather parameter on or others, and how the comparison between the result data Copernicus and incident data on the case strata prima incident based on the meteorological analysis after the incident. In the same ordinate, the incident report state that the wind speed around 8 to 20 knots. It is same like around 4.1 to 10.20 H, and then the wave height around 2.5 until 3 meters. Meanwhile, in the Copernicus data set, the significant height of combined wind wave and swell is 1.4 meter, and the wind component is around 1.9 meter per second. This is the Copernicus data set preview that, and then this is the meteorological analysis picture. And then the conclusion. The conclusion is the result of comparison between ERA5 and Copernicus data similar pattern or contour in some variable, for instance, in the wave parameter. And based on data before, this data, the Copernicus data relatively has a lower value than accident data. And then because of that, ERA5 Copernicus maybe can be used for preliminary weather analysis in contour or pattern of weather parameters in the Ferry incident. So it could be used as the preliminary analysis in the incident. And the correlation in the conclusion, I attach correlation with IWS and AIS integration program. The AWS and AIS integration program could help Copernicus do more accurate reanalysis by participating, storing, and sending the weather data from the integration that has been installed in the ship around the world. So this is my conclusion and correlation, and thank you.
Thank you.
Hello, ladies and gentlemen. My name is Reza Bagus Ramadan, and I'm here college, Joel Herdian Sesyawanto, and we are from the Institute Technology 10 November in Surabaya. So we will discuss sudden hazardous weather. Salah lagi. Ladies and gentlemen, my name is Reza Bagus Ramadan, and I'm here with my colleague, Joel Herdian Sesyawanto, and we are from Institute Technology. Here we will discuss sudden hazardous weather causing accident in Indonesia. So the first, we start with the ship accident data. We have reviewed archive data from the KNKT, or also as Indonesian NTSC, National Transportation Safety Command. And we reviewed more than 200 cases from 2006 until now. As we can see, in all cases are identified as the weather-caused accidents, with a number of 88 cases. And we data by analyzing each accident report and identifying cases as sudden hazardous weather-caused accidents, with a total of 31% of the weather-caused accident. From this data, we can see that sudden hazardous weather is an important topic to be discussed here in our workshop, especially for Indonesian water. Here we will present some of the sudden hazardous related accident cases that become the background of our research. The first is KM Lestari Maju. The accident was happened on 3 July 2018. The place in the Banda Sea, from the route of the vessel is from the Bira port in the South Sulawesi to the Pamatata port in the Selayar Island.
5 on the buffer indication of sudden hazardous.
The time of departure, KM Lestari Maju depart At 10 o'clock local time from Birapot in Bulukumba, South Sulawesi to the Pematata port, the Selayar Island. Based on the report, local weather authority report the wave condition at the time of departure range from
And ladies and
0.5
gentlemen,
until 2 meters. 2 hours after departure, at 12 o'clock local time, the wave condition increased to 3 meters with the wind speed ranging from 8 until 20 knots. At the time of the accident, the weather data information released by local weather agency had come from the Pauterip Maritime. There were indications of the bad weather, but the KM Lestari Maju didn't get information. The weather analysis. At departure, local weather agency report the wave condition at the time of departure range from 0.5 until 2 meters. At the accident, wave condition increased to 3 meters with didn't receive any early warning regarding indication of the bad weather. And for the analysis, the predicted rapid change in weather condition.
The second accident that we're going to discuss in this KMP Windu Karsa. The date of the accident is 27th of August 2011, and it took place in Gulf of Boni, which they were planned to sail from Bajo Port to Kolaka Port around 86 nautical miles. The time of departure of KMP Windu Karsa is 14:50 o'clock local time, and it sails on 26 August 2011 with 110 passengers with 21 marine crew, a total of 131 people and 25 motor vehicles on board, sailed from Bajo Port, southeast Sulawesi. The time of the accident is at 12:05 a.m. local time, and the ship capsized in the coordinates, and we can also see on the picture on the right side of the slide. And what really happened is sudden hazardous weather, and the ship took on water, tilted, and capsized. And the weather analysis before the departure of KMP Windu Karsa, it is reported as clear weather with 0.5 until 0.75 meter of wave height. But after 4 hours of crossings around 1850 local time, one of the ship crew reported that the weather suddenly changed from calm weather to rough weather with approximately 5 on the Bruford scale, around 22 until 27 knots. Later, investigators later found that the nearby vessel deck logbook reported also the weather, the same weather of when the area of accident, and it was reported 3-meter wave height with high wind speed. Our analysis is their indication of sudden hazardous weather, and it is failed to be predicted or to be anticipated. And the third accident that we're going to discuss here is Karamando. The date of the accident is 29 December 2016 and took place in Malacca Sea, which they were planned to sail from Ternate to Jailolo. The time of departure is at 28 December, and it is at 9:30 local time from Dufa Port. There was a warning before the departure. The AWS Maritime Ternate sent out a report of possible 2-meter average wave height with additional warning of potential wave height up to 4 meters. But the warning was reported via social media application Telegram and did not sent by radio communication device. And KM Karamando did capsize at 29 December at 11:30 local time. And it is caused by the sudden hazardous weather change, and the wave actually came onto the decks. The weather analysis is the AWS Maritime Ternate shown in the map on the slide before, located around 12.3 nautical miles away from the accident site, has already declared a warning of potential hazardous weather. Coromandel did not get the message because of lack of proper communication device. Investigators point out that there is a need in an improvement in communication equipment. Other ways to prevent such an accident are to maintain communication via radio between the ship and the Coast Guard. But by doing so, news about the position, weather information, or estimated time arrival can be submitted periodically. Or we can also use AIS, which is mandated by the IMO. The analysis of this case is the vessel apparently did not get the weather information because of failure in communication. Due to improper communication device, also there was a lack of attention from the captain. It is becoming quite clear that those three accidents that we discussed, that we need to improve two things to ensure the ship safety regarding to sudden hazardous weather risk. The first one is that sudden hazardous weather is hard to predict, and we need additional tool or additional data to predict such a phenomenon. But and the second thing is not only the weather data, we also need to improve and ensure the good communication line between the authority, in this case, the local weather agency, to the ships. Thank you for your attention. We hope that this research and this pilot project can be successful and implemented to other ships in the future. Thank you.
Hello and welcome everyone. I'd like to take this time to talk about our innovative low-cost technology for environmental monitoring.
Hi.
My name is Paul Kuchera, and I work with my colleague Martin Stinson
And Mom,
to develop.
Anthony, I just wanted to point out we need to insert Joel's presentation manually. So we'll take a stop because Joel needs to, and then we'll do Paul. Okay. So can you let Joel's screen share?
Of course.
His part of the presentation. Yeah. Thank you. A little break from the playlist. Thanks.
Okay, Joel. Okay.
Yes. Wait a second. And where are you? We're okie dokie. Thank you. Okay. Your co-host. And you're muted right now. Joel? Okay. Oh, you're screen sharing. Okay.
Hello, ladies and gentlemen. My name is Joel Herdian Setiawanto, and now I'm accompanied with one of my colleagues, Reza Bagus Ramadan, and we are from Marine Engineering student from Institut Teknologi 10 November, Surabaya. And in this occasion, we're going to explain about the installation of AWS, or Automatic Weather Station, on the vessel. First, there are two goals in this section that we're going to be discussing. And the first one is we're going to explain about step-by-step installation of AWS, or Automatic Weather Station, on board and the system used. And the second goal is to explain about collecting weather data and how to process the data. So what is actually AWS? AWS, or Automatic Weather Station, is an instrument that used to read some weather parameters such as wind speed, wind direction, temperature, air pressure, and so on. And this instrument will also be operating in 24 hours on the ship, and this instrument will record the data by real time. And here's the schematics of the system. First, we have the AWS, Automatic Weather Station. We connect with the RS-422 interface to our mini computer. and then we connect the pilot port cable via RS422 to the AIS. And this AIS will also transmit all the data through the VHF antenna. And before doing everything on board, we also do some trial installation on our lab. First, the installation process began in our lab, and this procedure to ensure all the instrument between AWS and the AIS is working properly before we doing the installation on board the vessel. And all the installation process is actually included on the guidebook, so we can do it by ourselves. And the installation connects all three main instruments that I already explained before: the AWS itself, the mini computer, and the AIS. And we can see the data, or we can receive the data via two connection right here. First, we have the RTL SDR AIS receiver. To do so, we track the AIS frequency first, and then after the tracking is done, we capture the frequency signal and the AIS have transmitted. Then if the tracking is success, there's some information on the interface, and we can also see the raw data from the AIS transmitter. And the second way to see the data is via a local area network cable or LAN cable. We can check the connectivity between the AWS in real time. We can also do some monitoring, real-time monitoring, using the RS422 dongle, and the weather information can be shown in the computer screen, as you can see in the image. And to connect the AWS to RS422, we can do jumper on the cable from the terminal on our mini computer. Based on our research, there are so many options for the route selection where we're going to install the AWS. So we choose one of them by looking some parameters such as home base. The second parameter is distance of the route. And the third one is the weather condition of the route. And from those parameters, we choose the route from Tanjung Perak to Kumai Port, where from Surabaya to Central Kalimantan, with distances over 327 nautical miles, and the duration of the route is 27 hours. And we gonna install the AWS as our pilot project to onboard the Dharma Kencana 3, and here's some general specification of Dharma Kencana 3.
All right, this is the outline we will talking about. The first is the installation, and the second is the setting, and the third is the collecting data. Okay, the first one for the installation. The installation starts with the mounting process for the weather sensor. It's carried on the top of the navigation deck. Weather sensors should be positioned far from any distracted communication instruments. And the truth is the sensor instrument must be mounted in the clear air, away from obstruction in any direction. For the mount, at least it's 1 meter above the deck. So this is the overview of the installation. Positioning of the weather sensor should be avoid any obstacle and any distraction from other communication instrument. The cable pass through to the existing penetration on the top of the navigation deck. After the weather sensor have been mounted on the top of the navigation deck, the weather sensor must be calibrated to adjust some parameters. We can also check the connection with the local area network cable from mini computer to the laptop to ensure the weather data have been transmitted using the PUT software. After finish the setup, the next step is connecting the weather sensor to mini computer using the existing cable, and then connect the MOXA to the AIS cable to the ship's AIS. So this is the overview of the installation on the navigation deck. And then in some cases, there are some problem with the AIS pilot plug connection to the mini computer. there is a reason for this situation, like there are some defect with the pins on the pilot plug. So the solution is using the bypass option is the alternative way to connect the signal transmit and receiver, the IS transponder to the mini computer in the directly. And the last is the collecting data. There are three ways how to collect data. The first is using the USB drive. Will connect it with the computer. And the second is the using satellite. And the last is using the short base as receiver, or basically is using the vessel traffic service. Thank you for attention. We hope this pilot project can be successful and implemented for other ship in the future.
Okay, I will continue my share screen, ma'am, everybody, to the Mr. Paul Kuchara presentation.
Hello and welcome everyone. I'd like to take this time to talk about our innovative low-cost technology for environmental monitoring. My name is Paul Kuchera, and I work with my colleague Martin Stenson to develop this technology. And we are part of a group called the University Center for Atmospheric Research, COMET, which is located in Boulder, Colorado, in the United States. As a little bit of an introduction, we established the 3D initiative about 8 years ago in 2014 to support disaster risk reduction programs. The goal is to design and implement sustainable observation capacity in the least developed data source regions. This provides early warning capabilities to reduce risk to the most vulnerable communities. And also provide a low-cost, innovative, sustainable solution for hydrometeorological related applications. Why 3D printers? So 3D printers are relatively inexpensive, can easily be attained in most places around the world, and it can print a wide variety of sensors that support the observation networks. We then integrate low-cost, reliable microsensors to measure the different environmental parameters, and the whole idea is to design a system that can be assembled locally. And then once that happens, you can then print and replace your components of your automatic weather station as those components fail. And just as a note, all systems eventually will fail for any kind of weather station. And then enable local partners to take ownership in building and maintaining observation networks. We currently measure a variety of parameters including air temperature, surface pressure, relative humidity, wind speed and wind direction, rainfall rates, and solar light. The data can be accessed through in real time or through a local data archive on the station. Resolutions are 1 minute or longer as needed, and a variety of communication solutions exist, including wireless, mobile phone, satellite, and low power long range communications. The cost of the systems to make are in the order of $300 to $400 US. And here's an example of some of the station deployments shown below from Barbados to Kenya. The current status of our 3D PAS network is shown in this slide. So 3D PAS have been deployed in at least 12 countries. We have additional stream gauge and snow depth sensors deployed here in the United States and also in the Dominican Republic. And part of our project and our program is to provide in-country training and knowledge transfer to establish fabrication facilities and get the networks established. And then just a list below are some of the countries that we've installed our stations in or plan to in the near future. So just to summarize, we've developed a low-cost observation network capability using innovative solutions to increase environmental monitoring capabilities around the world. This includes atmospheric monitoring for temperature, pressure, relative humidity, wind direction, wind speed, rainfall, and solar light. We also have a water level monitoring solution for stream gauging and snow depth monitoring. And we support a variety of environmental applications such as early warning that can detect flash flooding, storm surge inundation, and also for decision support applications such as water resource management, agriculture, and marine operations, such, for example, as ferry operations. So with that, I want to say thank you, and I hope you enjoyed my presentation.
Okay, thank you. Good morning and good evening to our colleagues in US. And
Anthony,
first of all, I
please
would like
pause
to
video.
introduce myself. My name is Bayu Idipratama. I'm from Marin.
Anthony.
Yes, sir.
Okay. This is for next session. So the last presentation from Paul, actually the last presentation for second sessions. Now,
Okay, sir.
yes. So we like to invite comments, questions, or other thing to discuss in following the presentation in the second sessions. So I would like to invite all participants, if you have questions or something in mind, please raise your hand, and then yes, please. Is there any questions?
I think Mr. Greg want to ask.
Oh, yes, please, Craig.
Hi, good evening. A question for Paul Kucera about the 3D printed weather stations. Very interesting. I'm curious as to what you're using for the actual sensors in the weather station. I mean, I see how you can 3D print the frame and the housings and things like that, but what are you using for the actual sensors for that system?
Yeah, thanks, Greg. Yeah, that's a great question. Yeah, so we're using these low-cost microsensors that are commercially available. Most of them are I2C capable, and then also using like for the rain gauge, using sensors just to measure the tips and stuff. So yeah, everything is very simple and easy to use. And what we do is we integrate those low-cost sensors into the housings that we 3D print, and then the way they're designed is if a sensor fails, you can actually just take one of those micro sensors out and put a new one in and continue monitoring. So making it as easy as possible.
Okay. So are there any other questions for our presenters? Captain
Well,
again.
yeah, thank you. It's not a question, just to thank the panelists in this segment, particularly Brian, Greg, and Paul. The reason why I want to thank you especially is you would know by now that the Worldwide Ferry Safety Association team have been working on both the AIS technology of the weather and the 3D presentations on making the weather monitors in Bangladesh, and we have been trying our best, trying to convince government and private organizations in Bangladesh to try and install those. And your presentation actually gave me a little more insight for me to speak or try to convince those people who are there that there's a lot of value towards that one. And with 3D printers, it can make it much cheaper than. So thank you very much.
Okay, thank you for your comments, Captain Urur.
Yes,
so
thank you.
I see Mr. Freddy raised his hand. Please, Mr. Freddy.
Thank you, Mr. Alex. It's excellent presentation for everybody, especially for Bayu, Anthony, and his colleagues from the Surabaya. My question is regarding the presentation from the Anthony and Pak Bayu. Since that you have the data, do you have any any plan to define and expand your data so that the web model for the Indonesian water could be created. So the designer and also the ship operator can also predict the weather in advance, and they maybe they will get some prediction by SAP, but they have to confirm their prediction by the forecast, maritime forecast from the BMKG. So I think since that you have the data, the huge data from the Copernicus, since 1979 to recent year is almost then maybe 30 years. I think it's a huge data from the maritime forecast. I think. And the second one is maybe is some suggestion from Bayu. If the like the Copernicus, so maybe BMKG could provided the limited public domain raw data. It's look like the Copernicus. So some researcher could use this data and compare with the data coming from the BMKG, Copernicus, or ECMWF for the research. Okay, Pak Alex, thank you.
Thank you very much for your question and suggestion, Pak Freddy. I was thinking that you may also convey your first question in the chat box, but it's all right. So we can save it for later session. Pak Bayu, I guess it's your time to respond Mr. Freddy's question and his suggestion as well. Please.
Okay, thank you, Pak Alex, and thank you, Pak Freddy. Nice to meet you again. And the first question regarding to in the chat box, you already mentioned about the definition of the high wave, right? So, in my opinion, that we can define the high wave as something that's very relative, right? Because, for example, at the MKG, we define the high wave warnings based on the Douglas scale, where wave height above 2 meter or in the category of moderate sea will be defined as high wave. And also at the MKG, we define the high wave warnings depending on the climatological data in that area using the percentile method. For example, Palik, could I share some slide?
Okay, so I'll let you be a co-host. Just please
Okay, thank you.
wait. Where are you? I think Roberta can do that. Oh, okay. You already be a co-host now. Please.
Yeah, thank you. Yeah, for example, as shown in that image, we can define the high wave warning in the southern Java and the northern Java will be different. For example, in the south of Java, the wave above 2 meters are conditions that continue to occur there. This is the data from 30 years reanalysis data from BMKG ocean model for BMKG wave model is in the y-axis to improve our model. Yes, BMKG. Maybe in the next my presentation, I will show you the next BMKG the BMKG ocean model. We will be implementing the couple atmospheric wave and ocean model, which is the between the ocean model, wave, and atmospheric model with 3 kilometer resolution. And also already assimilate with some data like a drifter and also the data from BMKG observation. Maybe in the next presentation I will show you. And regarding to to access data, already now BMKG have the open up access. So maybe later we can talk together. You can access the data from BMKG with OpenDAP, and also we now develop the API to get the more easy for user. Thank you, Pak Freddy.
Okay, thank you, Pak Bayu. It's good news for us that we could get some raw data from the BMKG. Since that in the past we only get the data from the ECMWF or from the NDBC NOAA data. So, thanks, Pak.
Okay, Pak Ferry.
All right.
But I have a question. Is it possible? Okay.
Yes, please, please, Pak.
Yeah. Maybe my question is not for a specific person, but I think based on this pilot project to connect the automatic weather station to ICE data is very interesting thing. Maybe we can write a recommendation to how to implement this project with the all vessel in Indonesia. As we know that some vessel in Indonesia have the automatic weather station also, right? They already installed by Airmar or etc. And we can push the ship company through the government how to integrate the data from the automatic weather station into ICE. On the other hand, as you know, BMKG also have a plan to install the 40 automatic weather stations during the next 2 years, and also we will agree to try to connect the data from our AWS to the ICE system. Maybe we need to make or to write one recommendation from this workshop, I think. Thank you, Pak.
All right. Thank you, Pak Bayu, for your comments, and actually, it's really good suggestions. First of all, before Roberta commenting on this session, I think we have a good point coming from this conference that BMKG opened his access to the BKI, and especially for research, I guess, right? So then, yes, and for the next comment from Mr. Bayu, yes, of course we can do that, but we can see that the challenge ahead can be very very big. So it means that we have to deal with numbers of different operators, different type of AIS manufacturers, and again we have. But still, we have to be very optimistic to make these things happen. That's the first thing we need to have at this point. Just because it's time very limited. So Roberta, you would like to say some words, please?
Bayu could possibly he could start his presentation for session 3, which is taking it to the future. So would that work for you, Bayu?
Yes. So following that, I think we can save all the question, comments, or advice or anything for the last question and answer session. So now we can move to the last session, which is will be delivered by Mr. Bayu, Catherine, and Dr. Greg as well. So please, Anthony, you can start the video presentations again for the next session.
Of course, Mr. Alec. Let me share screen.
Okay, thank you. Good morning and good evening to our colleague in US. And first of all, I would like to introduce myself. My name is Bayu Idipratama. I'm from Marine Meteorology Center of BMKG, the Indonesian Agency for Meteorology, Climatology, and Geophysics. And this session, I would like to deliver the strengthening of marine meteorology system in BMKG, which is the ambitious and feasible program to strengthen the capacity of observation and also modeling and also the dissemination system. Please let me to share my screen. So in the next 5 years, BMKG will have the ambitious and feasible program we call the strengthening of marine meteorology system, which is include the strength of the observation system, the ocean modeling and the production system, and also the dissemination system. And this the chart will be implemented in the next 5 years. If we look this picture, the observation system network and around the Indonesian seas, we will strengthen the capacity of the quantity and the quality of the observation system. For example, we will install the 40 units, the vessel automatic weather station, and also the marine automatic weather station, and also the SF coastal radar. And on the other hand, we also will be strengthening our capacity for the ocean modeling. We implemented the coupled atmospheric wave and ocean model with 3 kilometers resolution. And also we strengthen the integrated data management system and dissemination system to the end user community. And this map shows us the ocean observation distribution existing. Right now, BMKG have about 40 marine automatic weather station entire of Indonesia, and also we have 3 pairs high frequency radar for observe the surface current and also the wave height. And also we have about 18 ships vessel automatic weather station, and also one wave recorder. And this is our plan for next 2 years. The map of development plan of marine meteorological observation infrastructure. In the next 2 years, we will have about 30 drifter and 20 floats will be deployed in around of Indonesian seas, and also we will install the main automatic weather station, around 40 units in several ports in Indonesia. And also we will be installed the vessel automatic weather station. About 40 vessel automatic weather station will be installed in 2022 and 2023. This is the map of the distribution of the vessel automatic weather station, which will be installed in Indonesian seas. This legend is the color. The ship company, for example, the yellow one is the Pelni Shipping Company, and the red one is the Indonesian Ferry company. And this is the diagram of the automation. We will start the processing unit. The processing unit will be connected to the ship compass from vessel, and also connected to the satellite modem, and also connected to the several sensors like air pressure, air temperature, and humidity, wind, and also sea temperature sensor. And also the processing unit will be connected to the monitoring display on the ship. In the next step is improvement of the ocean modeling. In the next 5 years, BMKG will have the regional high-resolution regional ocean circulation model with spatial resolution 3 kilometers, and also BMKG will implemented the coupling atmospheric wave and ocean and coupling atmospheric wave ocean model, which is for the ocean model, we have ROMS, and for the wave, we have a SWAN, and for the atmospheric model, we have WAV, with a spatial resolution of 3 kilometers for ocean wave and atmosphere, and also the model will be adapted every 6 hours. And the next one is the strategy BMKG to improvement of dissemination system, or this session support system. We call the INA MARFES, the Indonesian Marine Route Forecast. The idea is how to get the information to stakeholder. For the first one is to get an easy to use information on marine weather on customer routes, and also to discuss the service route with customer, and also to manage the risk of avoiding extreme condition for the more critical cargoes. And also the last one is not this, to reconstitute the mid-ocean condition. And what we deliver in this system, we will deliver the user-friendly web platform to delivering professional weather data and document route forecast, and also a rolling 10 days weather forecast to anticipate the extreme condition to be avoided. And also an impact-based forecast on risk level and recommendation related to weather condition. And also possible to the constitution of particular day on precise coordinates, and also a statistical treatment of for 20 years of in-case data to determine the odds to find extreme weather on stakeholder unit. And it is the BMKG online maritime weather information system for marine transportation, and we call the INA MARFES is the multi-integration system within the several marine data, which is consists of the marine meteorology observation, the BMKG ocean forecast system, and automatic identification system, tracking system, and also fishing ground and port weather forecast. And also in this system, it's possible to have the document of marine weather route forecast, which is consists of route weather forecast, the port weather forecast, and also the impact-based forecast and recommendation related to the forecast. And the last one, not a list, but I would like to give some suggestion to next our development. Is the first one is there's need for system integration with automatic identification system, so that ship can monitor weather data in real time. And the second one is the integration with electronic chart display information system, or ECDIS, is required so that the BMKG forecast can be displayed directly on board. And the last one, but not least, is preparation of marine impact-based forecast. That's all. Thank you very much. Good morning.
Hello, I'm George Berg from the University at Albany, and I'm going to talk about technologies that allow us to improve our automated weather systems and our data collection and analysis. If you haven't seen the presentation by Paul Kucera earlier on innovative low-cost technology for environmental monitoring, I highly suggest you go back and take a look at that, because our work here much builds on that. Their 3D pause system is mainly terrestrial. We're actually aiming to extend this work into maritime environments, that is, ships and ports. Our goal here is to provide hazardous weather warnings, as well as just in general to increase the amount of weather data for weather and climate purposes. We overall share the same goals as 3D pause. We want these units to be inexpensive. We want these units to be sustainable. And we want these units to provide useful, actionable data. All right, I'm going to focus on technology changes. I'm going to talk about improvements in computers, improvements in sensors, and a little bit about improvements in communications. I'm also going to talk about the possibility of increased use of machine learning in the automated weather systems. First, to computers. In these kinds of systems, the computers are used to control the sensors, to gather the data from the sensors, process it as necessary, and then send it out to communicate the data to the outside world. In the past decade or so, we've actually seen rapid improvements in computers, that they're smaller size and that they're lower cost, low power consumption, which is increasingly important. And one of the nice things we've been seeing that'll tie into the machine learning later is increasing computational power. As examples, in the upper right, you see a Raspberry Pi and a Raspberry Pi Zero, which are more full-fledged computing systems, but still low power, and they're smaller than a smartphone, or in terms of the Raspberry Pi Zero, much smaller. In the lower left, we have an Arduino processor, lower level, but still very useful for these kinds of purposes. On the lower right, we have a Google Coral system, which is a little bit more powerful, and again, it'll come in handy when we talk about the machine learning. Similar to the advances in computers, we've got advances in sensors. We've now got increasingly low cost, low power consumption, and an increasing choice of the kinds of sensors we can use, for temperature, for humidity, including wind speed. We can also do cameras, flares, things like that. One of the nice things about the new generations of sensors is they're actually increasingly easy to integrate into the computers that we're using. Kusera and Steinson's presentation already covered communications, but we're seeing increasing communications options. This is particularly helpful while you're at sea and away from the terrestrial infrastructure for communications. The last thing I want to talk about is machine learning. Traditionally, because the machine learning artificial intelligence models require lots and lots of data, and they do lots and lots of computation, we typically see them in data or cloud centers. And so instead of having to do your data processing and maybe generate your warnings locally, you have to send them a great distance away. And so that requires a lot of bandwidth. That requires, just the data be sent. And if a hazard is found or a warning is sent, it could be half the way across the world from where you actually need it. And that results into some logistical problems. There are some possibilities there in hardware and software. Advances in new chips, the increasing computing power we talked about earlier, as well as advances in the software, the ability to take these machine learning models, train them, but then shrink them down so we can put them on the kind of computers we're talking about. This allows us to put these machine learning models on the kinds of systems that we're putting in to control our automated weather systems. So this allows us to predict the hazards and send them out locally. Well, thank you very much for your attention.
Hello, I'm Catherine Lawson, Associate Professor at the University at Albany and Director of the Albany Visualization and Informatics Lab. I've had the pleasure of working with the ferry safety community for a number of years, and today I want to share a vision for the creation of a supply chain for weather information, an info chain, capable of bringing all the parts together to flow critical life-saving information to the right place at the right time for the right price. There's been a growing interest in weather conditions at sea. Today, we're collecting weather observations with the AWS on the AIS. We're even using satellite imagery and artificial intelligence for maritime weather prediction. And as a result, there's an increasing number of AWS AIS operations that can provide ground truthing for NOAA, as we've heard earlier in this conference. Now, these same weather observations could be used to create onboard actionable weather alerts. And we know that there's a need for real-time detection of rapid changes in the weather conditions at sea, and even more importantly, to be able to transmit alerts to nearby vessels that are at risk, as well as providing that weather observations to NOAA. And it's also very important to consider the ferry operator community that has knowledge of what those threshold threats are. What are the wind conditions? What are the wave tolerances? What about weather drops, for example, for freezing spray? And of course, any combination of these threats that put the vessel at risk. Now, we've also heard today about these computing improvements that include microprocessing and the opportunities to expand these with the AWS on board, developing alerts and transmitting these alerts by the AIS to nearby vessels. In addition, archiving the alerts and the actions taken after the alerts are sent for future analysis. But we will need to also consider a training program to include these onboard capabilities. So what will be gained from an info chain? Well, first of all, would we be able to determine when the lack of weather condition information or incorrect weather forecast caused the loss of life, property damage, or the loss of productivity? Could we determine the extent that the alerts at sea could have on the impacts of outcomes on other vessels? Or, very importantly, determine the increase in bad outcomes due to worsening weather conditions at sea? And even consider that we could combine the landside weather observation system with the AWS and the AIS integration to even increase the size of the benefits. So what will we need to maximize these benefits? Well, we need a system that has low-cost equipment, like the 3D printed weather stations, low-cost AIS equipment, and of course, the use of open source code to reduce the cost of licensing. And what will we get from these systems? Multiple uses for this data. Onboard alerts for the captain and the crew. Alerts to nearby vessels who may not have the ability to have weather observations on their own vessel, but would have their AIS system running. And NOAA being able to get additional ground truthing opportunities. All of this provides us with a research trajectory that could modify alert thresholds going forward. And I would also like to say that while we work on this, there's the potential of using the info chain concept with other modes in addition to the water mode. Thanks so much.
I want to thank all the speakers. Yeah.
Yes. Go on, Roberta, please.
Well, I want to thank all the speakers. It feels like a love fest when I'm reading the chat box. What questions do people have? I think there's a lot of. I see that there's a lot of positive energy to enhancing weather information at sea, and the technology is there, the will is there, and looks promising, and lives will be saved. So right now things look good. What questions do we have? What do people want to say? Well, one thing I want to just add, what Kate Lawson mentioned, although she was speaking about NOAA, the information would go to the weather agency in each country, and I guess to the World Maritime Organization. So, you know, this is big. It will affect, you know, everyone as we keep making more and more monitors blanketing the sea. Any questions? If there are, well, first of all, Leigh, can you see raised hands? Because I don't see them right now.
Not. Mr. Freddy raised his hand again. Please, Mr. Freddy.
Yes. Thank you, Roberta and Alex. I have some comment regarding the Pak Bayuko presentation, since that for the impact-based for the maritime weathers as the plan for the BMKG in the future. I think we need to collaborate in each other for the stakeholder in maritime industry in Indonesia, since that I think BMKG already have the ocean model. In my work also, I have also the storm model. and we could collaborate and make some common ocean wave model that to be used for the impact-based activity as the plan from the BMKG. And also, I think the Anthony also have the use data and can get the create and define the ocean model in Indonesia, and we can collaborate with some also in the Alex and some the student from the ITS or some lecturer from ITS to conduct it these activities and support to BMKG. Thanks.
Thank you. Are there other questions? If not,
No questions. Roberta, sorry. If there's no question, I would like to make a final note, if you permit, once all the questions are finished. Thank you.
Sure. And I wanted to make a near final note. Thank the speakers for a very, very serious and complete, and I would say rich discussion. I know I'm going to go back and listen to all the presentations again as I write them up for the Lloyd's Register Foundation. There was just like this tremendous amount of information there and ability to learn. People presented very, very clearly and completely. So I applaud you, speakers. You gave it your all. Thank you very, very much.
Yeah. So Roberta, you stole my show. What I would like to have done is, on behalf of the Worldwide Ferry Safety Association Board, I would like to thank all the speakers. Excellent, rich, resourceful presentations. We all take from it. And I would particularly like to thank Roberta for the hard work and the zeal she has tried to organize such a wonderful workshop and a presentation. And thank you all. So I just wanted to finish there.
Okay, and just to let you know, the playlist for the presentations will be compiled and a link set out within a day. There's also a live streaming, and I think we'll get the link for that and send that out. And we'll also have the list of questions, and if there are any outstanding, we'll try to respond to them. So again, thank you all for taking time and participating in this workshop. It's important, it's valuable, and again, we thank you very much. No other words, we'll say good morning and good night.
Good night. May I say some words?
Sure,
again?
please.
Yes. First of all, on behalf, yes, maybe I would like to represent this government of Republic of Indonesia. I would like to thank you as well for your consideration taking Indonesia as a pilot project for this tremendous efforts. I mean, I can see it's very promising system, and then like Mr. Bayu says, and many others also supporting that in the futures that we need to develop more and more, not just rather than just finish at this point. So then, yeah, and in the perspective of this conference, actually, it's quite funny because some of my colleagues asking when was it actually start. So some people say it started at on 27, but I say it's 27 on American time, United States time, but it started on 28 time. So it's quite unique and quite confusing actually for some people. That's were even in the last few minutes ago, my colleagues asked me, "Is it already started?" No, it's already started 2 hours ago. Because they thought that it will continue until 10 p.m. in the evening. Wow, it's quite amazing. But for me, again, I can see this is quite good starting point. Not, I mean, again, it is not. We are not completing now, but it is a good starting point to improve everything and to develop something that will be beneficial for safety improvement, especially for Indonesian maritime society. You like to closing the ceremony formally, Roberta? Or Yes, please. I think you are the elder. Okay, please. That's normally how we do here. The elderly closing the
Yes,
ceremony.
well, I guess I always, a good conference isn't the end of the day. It's somewhere in the middle. We've done a lot of work. We expect to do more work. More work. We expect more collaborators. Some people joined that didn't register, and if they just send me a ferrysafety@gmail.com, they'll get the recordings and the link to the live stream. So we want people to continue to be informed, to collaborate, to send their ideas. We just want to see the globe blanketed with weather monitors and information that makes life safer for all of us. So thank you all for joining. Okay, take care.
Okay, thank you very much.
Thank you.
See you next time.
Yes, see you next time. Good night, everyone. Good morning.
Good morning. Thank you and bye.
Thank you.
Take care. Okay.
Thank you, everybody.
Thank you,
Thanks.
everyone.
Okay. Thank you. Thank you, Freddie. Yeah.
Bye-bye.
Thank you. Okay.